Many of the world's convergent plate boundaries show obliquity between the orientation of the boundary and the direction of relative plate motion across the boundary. It's exemplified by this part of Southeast Asia, where the plate boundary changes its orientation with respect to the direction of relative plate convergence across the boundary. So, as the plate convergence varies, what's going on in the oblique segments? Let's go and have a look at the tectonics around Sumatra. So here's Sumatra. Let's give it some context. We have the Sunda block over on the right-hand side, a continental component of the Eurasian plate, and on the left we have the floor of this part of the Indian Ocean, which constitutes part of the Australian plate, and the plate boundary runs down the trench following the red line. But let's add a little bit more information. Because running along the length of the island of Sumatra is a major fault, the Sumatran fault, and it separates the Sunda block from its own forearc. So what's going on here? And the relative plate motion across here is like this. So these arrows show the relative motion of the Sunda block relative to a fixed Australian plate. What happens in this area tectonically? To answer that, let's see what the earthquakes tell us. So here are the focal mechanisms. In the forearc area, unsurprisingly, there's thrusting. And those thrusts are moving almost perpendicular to the trench. In contrast, the Sumatran fault is strike-slip. The sense of strike-slip here is right lateral if we use the trend of the Sumatran fault to constrain the focal mechanism. So the Sumatran fault strike-slip, and this is what's going on in the forearc. Can we make sense of this pattern, and can we work out what the rate of displacement on the Sumatran fault might be? To do this, we can set up a simple vector triangle, and we'll use the northern part of the region to do this. So the rate of relative plate motion is about 6 centimetres a year along that trajectory. We can set up a vector triangle using the orientation of the Sumatran fault, which is strike-slip, and the direction of thrusting in the forearc. And we've chosen this area because the thrusting direction is orthogonal to the trend of the strike-slip fault. So it's a simple vector triangle to solve. Now we know the orientation of thrusting relative to the plate vector. The obliquity is 25 degrees. So that's all we need to do to solve the vector triangle and estimate the displacement rate on the Sumatran fault. And it's about 2.5 centimetres a year. So deformation in this segment of the plate boundary is partitioned into a strike-slip component and a thrusting component in the forearc. In the Java segment of the plate boundary, there's no requirement for partitioning because the plate boundary is almost perfectly orthogonal to the direction of relative plate motion. Consequently, right lateral strike-slip faulting occurs in Sumatra, but in Java there's no such large-scale strike-slip system. So as plate convergence varies around these arcuate plate boundaries, different styles of deformation can occur depending on how the convergence is partitioned.